So yeah, you'll definitely have a question like question two, where you'll have a bunch of concentrations and rate data. And so for a question like this, what you need to do is figure out the rate law for the reaction. And you're going to figure out the rate law for the reaction by comparing different concentrations and the corresponding rates of those reactions to figure out, okay, when this happens to the concentration, what happens to the rate? And we want to do that one at a time. And so we want to do that for A, we want to do that for B. If we look at the experiments, you'll see that for A, between experiment 1 and 2, the concentration of A looks like it quadruples. And I want to choose 1 and 2 because the concentration of B stays the same. I need to only have one variable at a time. So we're going to compare those concentrations of A and those rates for our first part. And then for our second part, we want to look where the concentration of B changes. So we're going to compare these two because the concentration of B doubles. And if we look, the concentration of A stays the same in that case. So that means I want to compare this rate to this rate for the second part of this question. So we'll calculate. Right, I gave you this equation. So basically, right, our concentration large over concentration small raised to the power of n, where n is our reaction order, equals rate large over rate small. So for A, if we take a look at A, I've got 0.492 divided by 0.0123 raised to the n equals 1.83 times 10 to the minus 7 over 1.14 times 10 to the minus 8. So we want to divide those two, and I think we're going to get 4 for the first one, right? Yeah, so we get 4 raised to the n equals, and then I've got 16 for this one. So 4 raised to what power equals 16, right? We know 4 squared equals 16. So that tells us n equals 2 for A. Now we want to do the same thing for B. So for B, we've got 0.0084 divided by 0.0042 raised to what power equals larger, so 2.29 times 10 to the minus 8 over 1.14 times 10 to the minus 8. Divide those two, and we've got 2 raised to the n equals 2. And so here we can see that this is a first order relationship. I double concentration, and my rate doubles. So here, n equals 1. So now we can write our rate law. Because we know the reaction order with respect to A and with respect to B. So we put those both together and give myself some more room. We can say the rate law for this reaction equals the rate constant times the concentration of A squared, because we found it was second order, times the concentration of B to the first power, because it was first order. And then there's our rate law for this reaction.
So whenever they're giving us like a data chart like that, we never assume that it's the coefficient that causes the n, right?
Correct. Yeah, if you're given a data chart like this, different concentrations, different rates, we have to find the rate law of that reaction. We can't just assume the rate law from the coefficients of the reaction. And in this case, it did match, right? If we take a look, there's 2A reacts with B. So in this case, it does match the coefficients, but that always won't be the case. Did the Blackboard Zoom link not work for anyone else? Yeah, let me know if there was an issue with the Blackboard Zoom link. I'm pretty sure I just copied it from Zoom, but I maybe missed part of it or something. Question 7 is next, right? Which species will have the greatest rate of change in concentration during the reaction, right? For a question like this, we just go to the coefficients. We go to the coefficients because if this reaction takes 1 second, this would be 2 molar per second, 5 molar per second, 2 molar per second, and 4 molar per second. Oxygen has the largest coefficient, so it's going to be reacting. The rate relative to oxygen will be the fastest rate in this reaction because I need to put 5 moles of oxygen through this reaction every 1 second. Only 2 moles of nitrogen, 2 moles of water, right? 4 moles of nitric oxide. So largest coefficient would have the highest relative rate. For question 8, right? Also, you'll see something like this. Right, if nitrogen reacts at a rate of 5.6 times 10 to the minus 4 molar per second, what rate will oxygen react in this reaction? So we can kind of go back to Chem 106 and how we compared our relative rates by using the stoichiometric coefficients. So let me just answer this question and I can answer those questions in the chat, right? 5.6 times 10 to the minus 2 molar per second, and that is nitrogen. Well, we're going to go to the balanced equation. The balanced equation tells us for every 2 nitrogen, we need 5 oxygen. So we're going to try to get nitrogen to cancel out. So I need 2 nitrogen down here, 5 oxygen up here, right? Nitrogen cancels out. We multiply by 5 over 2, and we should get a faster rate. So I'm going to guess, without doing any calculation, that it's B, because B is the only one that's faster. But just to make sure, 0.056 times 5 over 2, yeah, I get a rate of 1.4 molar per second, 0.14 molar per second for oxygen in this reaction. All right, so 2 questions in the chat, right? Does physical state affect the greatest rate of change? We know, like on day 1, when we talked about things that influence the rate of the reaction, right? We talked about temperature, we talked about concentration, we talked about how homogeneous the reaction was. And so, yeah, if it was a solid, the reaction is not as homogeneous. So that'll slow down the overall reaction, right? All of those things we talked about are in general for what would speed up a reaction. I'll add 27 to the list. And we can take a look at 4, right? Which of the following factors do not influence the rate of a reaction, right? So for question 4, we're looking for do not, right? Temperature increases, a catalyst will increase, surface area will increase, concentration will increase, a type of the container, I don't think that'll change, right? The rate of a reaction. So I would go with D for 4.
Even when we're talking about the volume of the container changing and whether it might factor the reactants or the products, does that have any effect on the reaction rate?
I mean, I see what you're thinking, but it didn't mention that. Because certainly, yeah, pressure and volume can change concentration, but in the question, it didn't say like a smaller container or a larger container. So because the question didn't say, it just said the type of container, because we definitely know A, so number one, there has to be a correct answer. Temperature increases the rate of the reaction. A catalyst increases the rate of the reaction. The surface area increases the rate of the reaction, and concentration increase the rate of the reaction. So by default, I'm going to kind of go with D. I do agree if it said a smaller container or larger container, like because that would change the volume, which would change relative concentrations. Yes, but they didn't say anything more than that. So that's why I would go with D.
Thank you, that makes sense.
Yeah. Right. So Sarah, you're thinking of when we get to equilibrium. When we get to equilibrium, that's when we ignore solids and liquids. All right, question 10 and 11 are up next. Question 10. Yeah, so for question 10, right, we get the following information and the key. This came up in office hours. People were asking about this, how to solve this problem, right? The key to this problem is the following data was collected for a first order reaction. So it tells us this is the first order reaction. So that tells us, okay, natural log of concentration at time t equals negative kt plus natural log of concentration at time 0. We want to find the rate constant for this reaction. So we're going to say, I'm going to use this concentration as time 0, this concentration at my time in the future, and it happens to be 5 seconds in the future. So, all right, natural log of 0.0607 equals negative k. We're looking for my rate constant, right? Because rate constant is k times time, 5 seconds, plus natural log of my initial concentration, 0.1. Go through, do the natural log of all of those, 0.0607. All right, minus 2.8. Minus 2.3. Add this to both sides. And we get a negative 0.5 equals negative k 5 seconds. Divide by a negative 5 seconds. And hopefully, oh, it's going to be close to 1. I wonder why I got, yeah, 0.00998. I'm going to say it's probably because based on how I rounded this or something, I'm dropping something. Because we really have minus 28018, and then I add to that 2.3025. Yeah, and so there I get 0.4993, divide that by 5. And yeah, I get 0.0998 for that rate constant. And it's first order, so inverse seconds should be our units. But for that question, right, they tell us it's first order. We want to use the integrated rate law for a first order reaction. That's the key to that question. And then kind of based off of that, right, we found the rate constant. Now they want us to find the concentration 20 seconds into the reaction. So this is the one that's a little bit tricky. Based on our information from the previously, right, it's still first order. So natural log of concentration at time t equals my rate constant, right, negative rate constant, 0.0998 inverse seconds. we want to find this new concentration 20 seconds into the reaction. And my initial concentration is still 0.1. So natural log of concentration at time t equals, we'll multiply that times 20. And I get negative 1.997. And we get negative 2.30. So I get natural log of concentration at time t equals a negative 4.2997. And right, our concentration equals, remember, if we have the natural log of A equals B, well then E raised to the B is going to equal my concentration of A. So E raised to the negative 4.299 is going to give us our concentration at time t. So we need to get rid of that natural log. So raise E raised to that, and I get 0.01357. Let's see what we have. And so yeah, I would go with choice B here, 0.0136 for my concentration, 20 seconds into this reaction. I'll pause the recording there and I'll answer Sarah's question, and then we'll get started with the second group. The second group will be 14, 15, 16, 17, and 19.